Anand sir and Senthil sir, are we good to start?
Yeah, I think we are.
Yeah,
Okay.
we are good to go.
Okay, sir. Thank you. So, a warm welcome and good afternoon to all of you. So, today is the most awaited and an interesting webinar. I think we took out some time to, to host or, to schedule this webinar because it was a most important topic. And for the first time under Startup Mitra initiative, we are hosting a webinar with the two expert speakers. So, firstly, like we are so fortunate enough to get two experts at the same time and then the same day. So, I would like to welcome you once again to this webinar. And this today's webinar is on a post Silicon validation and manufacturing India capabilities. So, as you all are aware that this webinar is hosted under Startup Mitra initiative, and it is one of the initiative that we took, 2 years ago, and we are helping out the startups in a various schemes and with the various topics. So today I would like to introduce two speakers. So they are I can say esteemed speakers who took out their time and to come to this webinar. So I will take few minutes to introduce about the speakers. So first is Mr. Anand Mutaya. So he's a graduate from BIT Bengaluru and a postgraduate from University of Florida, majoring in solar cell manufacturing technology. He has an extensive experience and knowledge in digital test, hardware design, and value description. So currently, sir is working at TESOL as a VP. So I welcome you, sir, and thank you so much, for accepting our invitation. And next we have Mr. Senthil Kumar Damodaran. So sir is a postgraduate from Anna University in Real Estate Design. In his experience, he has a very well established track record of assembling high performance testing teams. And currently, he's a director of engineering at Caliber System. So I welcome both of you to the session, and I request you to take it up. And one request to all the participants is to mute yourselves. And whenever there's a session going on, and if you want to raise your questions, please take it up in between only, because since we have two speakers and we will have a presentation along with the Q&A. So request you all to mute yourself right now, for the easy flow of the session. And I'm sure it will be an insightful and things. Thank you so much, sir. So over to you, Anand, sir.
Thank you.
Thank you very much, Gautami. I would
Hi.
like to start the session by thanking IESA for giving us this opportunity. I also want to emphasize the fact that this being a startup mitra, so whatever Senthil and I are going to be presenting today would be more helpful for design oriented or design companies which are looking for post process
Anand, sir, you want to unmute? Can I request you to unmute?
Okay, I am unmuted now, right?
Yes, sir. Yes, sir. Please.
Okay. So most of the established companies or established semiconductor manufacturers in Bangalore already have teams or multiple teams working on post silicon validation. This, I think, session is going to be more helpful for either new startup companies or just design oriented companies who want to start pushing their designs into manufacturing. As This is a two-part session. I think holding on to the end to ask questions may be difficult. So if you guys want to ask questions in the middle of the session, I am welcome. You are welcome to do it, and I will be able to answer it. Okay, let me start the session. Are you able to see my screen?
Not
Hello?
yet, sir. Not yet, sir.
Okay. Let me try again. Now?
Yes, sir. Yes, yes.
Okay. So, as I said before, it's a joint session between Tesol Semiconductor and Caliber Interconnects, and thanks to IESA for hosting this session. Uh, we have a broad agenda. This agenda covers both Senthil's presentation and mine. We would like to start this with telling what are the post-silicon activities, what are pre-volume manufacturing activities, and what is Tesol's offering here. There is also a high volume manufacturing flow, which we also call the test and manufacturing flow, Caliber's offering, and we are open to questions either in the middle or even in the end. Suppose silicon flow. Uh, for people who are in the post silicon service industry, we know what it is. But people in the design industry, for them, post silicon is something that starts right after the GDS is taped out. Unfortunately, the post silicon validation guys, we look at it differently. For us, post silicon activity starts after the wafers come out of the fab. So in the manufacturing flow, there are two flows. One is the wafer manufacturing, and then the processes after wafers are manufactured. So today we will be talking about activities after the wafers come out of the fab. See, there is a pre-manufacturing flow, and then there is a test and manufacturing flow. I will be covering the topics on pre-manufacturing flow. We will be talking about a little bit about what are the pre-silicon take cares that need to be done for post-silicon activity. What is the design validation flow? What is quality and reliability flow, failure analysis and debug? And Senthil will be covering these topics, and I think about test challenges, test and manufacturing flow challenges, test systems. So he's going to go talk about the high volume manufacturing flow. Pre-silicon take cares. What should before I tape out my GDS? What should I have taken care of before the masks hit the fab? First of all, when we start silicon validation and manufacturing test planning should start during design architecture itself. Test cannot be an afterthought, especially in this world, today's world, because these devices pack so much of power and so much of capacity in them. You cannot think about test after tape out. It should start at the design architecture phase itself, because the test is a significant cost in your device cost or device manufacturing cost. If you do not plan for this well ahead of time, you could end up spending more to test than what is needed, or where it could be a challenge for you to sell product in the market. Because today, if you look at the industry, almost all companies use the same engineering tools, so the cost to the company is the same. The fabs are all mostly outsourced, so the cost is more or less the same. One of the differentiators is the test cost. So if you plan for your test in advance, you could have a upper hand in the marketplace. And in the today's world, test the design is completely packed, right? If you look at zero point 0.3 nanometers, if you look at 3D technology, if you look at 2.5D technology, there is very little scope for physical debug. Or if you go back to 15-20 years ago, pico probing kind of debug, those activities, there's very little scope. So your architecture has to plan for contactless debug. You have to plan for it. In case you want to debug any interface, you see how you could do it by just reading out registers, or having some bypass options in your design, scan options to read registers, to read contents of registers, to check any of your IPs. So plan for contactless debug. Anything you want to do physical debug, even using a scope or a multimeter, takes a long time, both for setup, and your hardware may not be compatible to do it. So contactless debug is the way to go. You also need to think about what are the IPs that are there in your you're going to be incorporating into your design. What is the test plan for those IPs? In today's world, to reduce the time to market, people or design houses get ready-made IPs, either soft IP or hard IP, and integrate it into the design. It is not just necessary if you get a functional IP and integrate it to design. You also need to know what is the defect coverage data. You need to ask your IT provider to give you all the test data and the defect coverage data, because at the end of the day, when these IPs are put into your design, if they do not have coverage, good coverage, this could be the weakest link in your test coverage. Sometimes there is always
Pause for
people.
you, Jessica. Kamala Harris has not declared defeat yet. If
Gautami, can you please? Yeah. So if you sometimes you get pushed over telling, hey, it's a very small IP, there's only few hundred transistors, it's okay even if it has a less coverage of 80% is fine, 85% is fine. But these small IPs, in general, you will have a lot of them across your design. So if you take an IP with only 0.8 coverage and then you replicate it 100 times in your entire SoC, your coverage, you will never get it up to the 99.5% you are looking for. What are the interfaces and what is its test plan? Right? For interfaces, in normally most of your production or high volume manufacturing test is geared towards defect capturing or finding defects and eliminating devices with a defect. But it is not necessarily verifying the complete functionality of your chip. Your silicon validation test plan should be geared towards full validation of your functional validation of your chip. So you need to start thinking about your validation plan even at the architecture level. If you are going to do functional validation on silicon in the DV environment, you also need to plan for what is the manufacturing test plan for these interfaces. As you most of you are aware, you are talking about interfaces like SerDes, which is 53 gig, your PCIe 32 gig. These are not things that you could test directly on a tester. So you need to have capabilities or ways to test these things in manufacturing. Manufacturing is not necessarily a functional test environment. It is more of a capturing environment. What are the parameters that are going to be guaranteed by design? You already need to have a list for it, because there are some things which cannot be tested either in a functional environment or even in on a tester. For example, if you're looking at the capacitance of the input gate, or if you're going to look at your termination resistor, directly trying to measure your termination resistor, which is inside the die, those things are not testable on a tester. So you should have the list of guaranteed by design, because those things should be checked in your simulation environment and not necessarily in your test environment. What are the parameters that will need silicon characterization? Because when we say silicon validation, you're talking about functional test. When you say silicon characterization, you would be talking about electrical characterization. Or which interface would you need your setup time, hold time, rise times? How are you going to check that? Things like that you should have already know during your design architecture phase itself. We also need to plan for what tests going to high volume testing, because high volume testing is where your test cost, you could throw your entire simulation test suite into manufacturing, but would it add any value? Would it catch any unique fail? Because in test high volume testing, you're always trying to use patterns, or you're always trying to use tests that catch unique fails. If five tests catch the same fail, you're not adding any value. If you're going to add five tests, you want them to catch unique failures. So you need to know you need to plan for what is the high volume test content. DFT, what are the DFTs you will have in place? Do you need a protocol testing on the tester, or do you want to use patterns to do protocol testing? What is the amount of patterns you need? Because not all testers come with unlimited memory. There is always constraints on pattern depth. There's all test constraints on tester capabilities. So these are things that you need to think about during your device architecture. What is the choice of ATE? See, in established companies, they already know what ATE they are going to be testing the device on, so they try to design devices for those ATEs. There are some companies that will do a test on reduced pin count testing. There are some companies which have unlimited of a pattern for pattern depth, so they don't mind loading up patterns or topping off patterns as much as memory they have. But not everybody has that luxury. So you, during the device architecture, you need to know, or at least you need to have an idea of what tester you are going to go to. So these are some of uh, the post silicon validation care abouts that you need to do during pre silicon. Is there any question here before I move to the next slide? Okay, I'm moving. So what is design validation? So design validation is basically, this is this is the step where you are going to verify on silicon, because design validation is already done in pre-silicon in your simulations. But there, it is very difficult to do a full chip simulation. You always do these simulations in parts, in partitions, and many times IPs and some of the features are black boxed, where you assume a certain that function is happening. But this is the first time where you are going to be testing a full chip silicon. The design validation on silicon is where you're going to be testing your design, full chip design, right? uh, so here, many of the companies, you will start with almost blind build devices, because when the wafers come out on day one, everything for everybody is, it's for the first time. The probe cards are going to be tested out for the test time. The test program running on silicon is going to be tested on the test time. Everybody has when wafers come out, everybody's in a hurry to start looking at, hey, are things working the way we designed? So validation team normally will start off with either blind build devices with no testing, or maybe a basic testing on the ATE testers. Basically, you may have just a continuity check or a power supply short check done, but you get your devices as blind build and not tested. So what does that mean? That means you need to have 100% pre-silicon verified content. If not, it becomes a chicken and an egg situation. Either is it bad silicon that you're looking at, is it a bad design, or is it bad content? So if you run into this vicious cycle, we can never make progress. So it is always recommended to go with 100% pre-silicon verified content. If your it is very easy to ask for 100% pre-silicon verified content, but when you're running simulations in simulators, it takes a very long time. So you should have a plan in place where you start verifying with verified you start verifying silicon with verified simulation content first. Then hardware, we should always have verified hardware before silicon comes, because hardware is the longest pole in the tent in any of our activities. You have hardware for functional verification, electrical verification, validation, SLT, which is, each one needs its own hardware. You need hardware for debug. What is this hardware for debug? Sometimes you may need certain pins to be pulled out for verification, or for scoping, or multimeter voltage check, things like that, which may not be there in your production hardware. You may need hardware for that. In multi-chip dies, you may find, when you're debugging a multi-chip package, die package, something is not working. One die may be, because both the die have to work for your package to be functional. So which die is not working, you will not know. If you do not have the right contactless debug options, you may have to put these die in a single die package, which is basically another debug package, another debug hardware. So such hardware needs to be built. Sometimes you want to do either an e-beam or an hotspot or things like that. You need to have hardware, separate hardware for that. You need to build hardware for qual, you need to build hardware for ATE. It's okay to build all of this, but we need to verify this even before silicon arrives, because on the day silicon arrives, if you're going to verify hardware and find there is a problem, uh, it is going to jeopardize your schedule by a long time. It is I guess it is, with all of this caveats which we have, it is always good to have a test plan and the flow ready before silicon arrives. You need to know what test you're going to be testing first, what is the expected result, where is the units coming from, where are the units going to go after you, because right during silicon validation phase, your quality guys will start already looking at needing parts. So we should have a test plan and a flow in place even before silicon arrives. Most of the manufacturing tests that we have today, or that the industry follows, is structural testing, scan based or BIST and things like that. But big SOCs need functional testing also. So we need to have a plan of what functional tests need to be ported to ATE. What are the scripts that you need to have to port these functional tests to ATE? There's a big difference between how DV does functional test verification versus what will happen in an ATE. In your DV, your system does all of the booting, system does all of the power up, it does all of the sequencing, it does all of the data flow. But in a tester, you don't have that. Tester environment is totally different. So the same DV content needs to be ported to ATE. So you need to know, you need to have a list. Normally, in established companies, they have a legacy of tests that they know that they need to add for functional verification. So you need to start building up that repository. And when you do your silicon validation or silicon bring up, you may be doing it on one or two pieces of silicon, but in reality you have to do the same validation across split across multiple devices. When we do splits, I am talking about silicon skews of fast lots, slow lots, nominal lot, typical lot. If there is a multi-chip modules, then you need to have a combination of these. So your time for validation is quite a bit. So instead of so you have to have a plan for scalability of how are you going to shorten your validation cycle, or how are you going to shorten this validation path, because you need to release silicon to production very soon. Electrical characterization and correlation. What is your normally when you do a functional validation, you're only looking for workload, and you're going to look at an output of the workload. If the workload is a graphics workload, then you are going to go look at your monitor or screen grab and see, okay, what is the image displayed, was this what you needed, was it what you had. If it's a PCI interface, you're going to talk to a PCIe end endpoint. You're going to verify some external devices that are connected to this device in functional test. But electrical characterization is totally different. Electrical characterization is where you're going to look at the electrical parameters of your signal. What is the rise time? What is the setup time? If it's a DDR interface, if it's a SerDes interface, what is the bit error rates? So if it is what is the if it's a very high speed interface, what are the eye widths, what is the eye opening, what is the jitter, things like that. So for all of this, you need to have your fundamental scope and multimeter kind of an environment, a bird scope multimeter kind of an environment. You also need to start worrying about correlation. What does the ATE data correlate to in terms of speed or voltage versus what my system is showing me in terms of speed and voltage or power, right? So these are some of the things you do in silicon validation. SLT, today's world, in the 5 nano post 7 nanometer technology, 753, everybody in the digital world wants to have some kind of an SLT. What is an SLT? It's a system level test. That means you take a part that is already tested on the tester, found to be good, you put it, you make it go through a functional test in production. Means every device has to go through this. When you do a validation check here, you're only doing it on few first article silicon or few SKUs. You're not doing it on every part that is going to go to the customer. But SLT, every part needs to go to the customer needs to be tested as a functional verification. So you need to get some of the content which you feel is going to catch unique failures which test ATE will not catch, but you have found a design weakness that you want to make sure your device passes through that before it reaches customer. So that is a very simple form of explaining an SLT. So what tests need to go to SLT need to be taken care of, and you SLT would catch failures for you which ATE did not catch. So you need to have a path to correlate to take the test collateral and convert it from an ATU to bench or bench to ATE. So you need some scripting, you need to have some kind of an algorithm that can take any test content from an ATE, convert it into a content that can be verified on the bench as a functional test. The other way around, take a functional test and you should be able to run it on a ATE. So during the correlation process or during the SLT process, when you have these failures, this is a very important step. So these are some of the things we do in terms of design validation. When it comes to scaling, right? Normally, when you do a design validation, you are going to be talking to the device internals. So all of your confidential information, your IPs and all that, you will have to expose it to people if who are working on these chips. So the initial verification is always mostly limited to the employees of the company, but when you want to scale, you could use services company like ours or the Caliber and people like that to scale the validation activity. That way you don't have to do all of your SKU testing yourselves, which if you can use the services of other companies, service providers, you could reduce your time to market very soon. So for that, TestSolve has a capability for post silicon and SLT validation lab. We have about 100 workbenches. So imagine if you have 100 workbenches, if you are going to use up maybe 50 workbenches, you can be testing 50 SKUs or of your silicon at a time while you are still bringing up. So basically, you are reducing your validation time. No, most of the time the first article will need debug, but when you are going to do your SKU checks, your verification on different configurations and queues, you expect most of the content to pass. So the debug effort on this could be less, but irrespective of it, you still have to validate it. So you could use companies like ours to do this validation, and we can scale up or reduce your test time to market pretty quickly. This would be on your validation side. For your character electrical validation, see all of these bench equipment that we talked about, right, is very expensive. So if you're trying to get a BERT and a DSO for a 70 gigahertz oscilloscope and a 64 gigabaud BERT, this runs into millions of dollars. So if you're going to invest on this, your ROI on a one chip or two chip will not justify the costs. So we as at TestSolve have the capability to do electrical characterization for all of your IPs, all of your boards, and all of your interfaces. So this is the electrical validation lab. This is the electrical validation component equipment that you'll need for doing EV. Any questions so far on validation? Okay, let's move to the validation and characterization part is normally, depending on your SOC size, 12 to 14 week kind of an exercise. But between the 12 to 14 weeks, if you have any design flaws, if you have any sensitivities, the expectation is you should be able to identify those and get your silicon ready, or get your next revision if there are any defects. Next revision silicon database is ready. While the validation is happening, one of another important activity will start in our pre-manufacturing phase, which is quality and reliability. What do we mean by quality and reliability? Quality is a zero-hour property, meaning its measure is in DPM. When a customer receives a part, is it going to work the minute he puts it in his socket? That is what quality personifies, and it is measured in defective parts per million that a manufacturer ships to a user or to a customer. The expectation is zero, but in reality, it's not. There are many different standards for quality. A JDEC standard, an AEC standard, a MIL standard, and GIS. What does that mean? When we do our quality checks, or when the device goes through the quality qual flow, there are different standards to which the tests are done. The JDEC standard, the AEC standard is very tough one because it's an automotive standard. Military, as because it's a military application, they are going to be higher than any of these standards. JDEC is the normal standard that we follow for consumer devices. What is reliability? Reliability is nothing but quality over time, meaning it's the mean time between failures. That is the measure for reliability. So the device could work the minute you put it into a socket, but some of them may fail. It may fail after a year, may fail after 2 years. So every device in the data sheet, you have a rel- uh, uh, time to failure spec in there. Some devices, you could say, like the high performance compute and home appliances, mobile applications, their lifetime is about 5 years. Appliances, consumer electronics lifetime is about 10 years. Automotive, the lifetime is about 15 years. So we do checks on the first silicon to make sure the material and the processes that we have chosen can live up to the expectation of whatever standard this is. Okay. One more important thing about this is always have a qual plan A and a plan B in place always, because anytime you find issues in qual, especially electrical issues or package issues, you may have to end up going and re-engineering something in your process. That would mean you will have to make some changes to your all the way to the base layer of your wafers, which would reset your entire cycle. So before we go to that, we should always have a plan B. Either look at your stress conditions, look at your domain that you're trying to target, so things like that, or look at an alternative qualification plan, or start lots, multiple lots qualification if you know you have some issues. This quality is actually four. There are four legs to it. The first one is called an accelerated environmental testing. These are the tests that you do in accelerated environment testing. Sorry, I because of lack of time, I've been have go fast on this. I'm just if there is any question, stop and ask me. Otherwise, I'm just going to try to go faster. You always start with preconditioning. Preconditioning means just you make sure your device is good, device and your package is good before you start the qual activity. All of this accelerated environmental testing is geared towards verifying your package. So when you have surface mount devices, what happens is it gathers moisture while it is on the test floor. When these surface mount devices are mounted onto a PCB, it goes through multiple temperature cycle flows. This moisture in the package during those flow will become vapors or water vapors, right? So that could damage or it could cause a popping effect inside your package. So to verify how long your product package can be exposed before you see any of this popping effect is what the tests are geared for. So in a preconditioning, what we do is before you start doing all your qual test, we need to bring the device to a nominal mode, meaning the MSL mode, which is the moisture sensitivity level should be set before you start any of these tests. There is a JEDEC spec for all of this moisture sensitivity level. Normal consumer product is moisture sensitivity level of 5. Okay, so these are some of the tests that you do. THB is temperature humidity bias, where your devices are soldered down to a carrier PCB and put in an oven with high temperature and humidity and in a bias condition. So it is electrically biased and put into an oven with high humidity and temperature. Or you have the next thing you have is the B HAST and the U HAST is high, HAST is highly accelerated stress testing, where you are going to be taking up the voltage beyond the nominal voltage to the max capable voltage of the device, both in the biased state. B HAST is biased HAST, U HAST is unbiased HAST. The device is just sitting there in the ovens, but not under bias. Then you go do something called a temp cycle testing. Here, temp cycle testing is where your device is put into different zones of temperature. When material goes from one temperature to another temperature very quickly, like -4 -10 degrees to 50 degrees or -10 degrees to 100 degrees in a very quick time, there's stress involved on the package or on the material. So we are trying to look for how this material handles stress. Then power temperature cycle. So the same temperature cycle with the device being powered up. Then high temperature life cycle and low temperature storage life. So these are some of the accelerated environmental tests done. This is basically to verify the integrity of your package, the integrity of how much moisture or how less moisture your package absorbs, how it boards to the manufacturing flow when the surface mount packages are mounted onto PCBs, and what are the effect of the thermal profiles on them. The next qual activity that we do is on your assembly activities, where we look for wire bond shear test, wire bond pull test, or a solder bump or solder ball shear. So these are all related to package and assembly issues, because it is in the see, once the package is manufactured, you dice the die and put it into a package and bond it. So what we are looking for here is with the wire bond shear, what is the integrity of the ball or the contact between the wire and the pad. How good is that contact? That is what this tells you. This test will tell you what is the strength of the wire between the pad as well as the package fingers. So this will tell you that integrity. So different tests will tell you about different parameters. The last one is the lead integrity. Basically, you want to make sure when you're putting the part or soldering down the part, the leads do not start bending due to temperature or deforming due to temperature. So these are all the qual assembly activities that we do. Accelerated lifetime simulation. This is activities that we do to verify the silicon process. These are all for the silicon process that we have chosen, or the fab that we are working with. Basically, your high temperature operating life, where you are going to run the part at a in a high temperature chamber for maybe 24 hours, 36 hours. Each one has a different read point. ELFR, which is early life failure rate. You're trying to, you will be, this is actually similar to what burn-in is, where you're going to run the part at a highly accelerated voltage, high temperature, uh, to make sure you have no early life failures. And then you have the soft error rate testing. You run the part 1,000 times and make sure it at a low voltage and make sure it always passes and there's no soft errors or any memory errors in there. Short circuit test, you basically physically short the output of the device and make sure the device, there are enough protection built into the device where the short circuit would not kill your device. Similarly, EDR, which is data retention rate test. So all of these tests are done to verify the integrity of your silicon. And then you have the electrical tests, which is basically ESD, latch up, EMC, and DD. Most of any design issue, anything that your design validation team finds would be related to your RTL, would be related to the functionality of the chip. Any anomalies, quality and reliability finds is basically a issue with your process. So well, any issue we find here needs to be addressed immediately, which would sometimes mean engineering the process again or engineering the transistor again. And most of these electrical verification is a combination of your process as well as your design. Okay. Different JDEC different specs would make you treat each failures differently. Not only the failures, even if a small thing changes in your process, in a small change in your process window, you may have to redo the qual. If there is a small change in a material that you are sourcing from the different, if you are sourcing material from a different vendor, you need to go through the qual process for a different vendor. If there is any change in even any process parameter, you may have to go through this qual process again. So qual is very tedious, expensive. It may take anywhere between 10 to 14 weeks to build all the qual hardware, 10 to 12 weeks to do the entire qual process. Basically, the qual system, the reliability system is setup. This is how the setup is. You always have a test vehicle. Sometimes even before your silicon comes, if you have a device which is running in the same process, you could use that as a test vehicle. But at the end of the day, you should still run your design through a reliability test to address failure mechanisms, where basically here it is your device in your package that is going to go to production. There are two kinds of testing. One is taking a device to failure. You are going to go keep overloading the device until the device fails, like a ESD test, like a latch up test. Even though you would want to see where the failure occurs, you could spec the device to a 2000-volt ESD capability or to 3000-volt capability, but you will take the test to see where the failure happens. If the failure happens, is it right at the border, or is it far enough from your spec. The reason is, if it is right at the border, you could always forewarn your assembly houses, your PCB assemblers, hey, my device is spec to 200, it will fail at 250. So make sure your processors are tight enough to not go beyond 2000 volts. So things like that needs to be put in place. So these, that's why you take these tests to fail. There are other tests that we do, which we do a test and we check. So basically, electrical wire stress, the wire bond stress, the SAM and cross sections, we can go do a test and go figure out using these tests if you can detect any failure. Then there is some electrical characterizations you could do to go see any shift in process or shift in parameters, like a threshold shift or a contact resistance shift. If there is a crack, uh, if there is a crack in the die or in the package, does it keep changing with more stress we apply? And then we go find out what the failure modes are. Basically, is it a bond lift off? Is it a parametric shift? So basically, the qual setups, different tests have a different way of generating the failure mechanism and generating the defect. What is the use of just finding out that we have a defect? You need to have a failure analysis capability also. Failure analysis, actually, whatever I have typed in here is on the picture replicates the same. You should have an electrical analysis because that's the easiest you could do. Visual inspection is next step. After that, you go through the physical physical failure analysis, where you have to delete the part. You may have to remove the die from the package and you have to reattach the die. You may have to do some e-beam or fibbing, pico probing. So this basically is the step-by-step approach of any failure analysis. What does an optical microscope give us when we do failure analysis? Basically, these are the non-destructive examples. We will also talk about destructive examples. If I want to go look for any package damage, if I want to look for cracks or blisters, discoloration, solder bridge, an optical microscope would help me detect that. If you find nothing in there, or if you have failures of different kinds, an x-ray vision will help us determine that. If there is any shorting in the micro bumps when I do a reflow, or if there is any, if this is an 2.5D package, if the die inside the package is shorted, so is that why I'm seeing failures? I could also look at cross sectioning of the package to see if there's any cracks or any anomalies. So x-ray would help that. SAM is another kind of technique where I could SAM is scanning acoustic microscopy, where I could take the failing part or the part that has a problem and do a SAM on that, which would give me basically any voids in the package or any die crack or any bond or lead peel off, things like that. All of these will give us indication of what the failures are, what could be the reason of failures. So these are non-destructive examples. When you get a bad die, what you could do before you go into a destructive or an physical FA. Semi-destructive would be you open up the area of the package, which we call a decap, where you suspect the failures to be. You can take an IR image or you can do an imaging of the die. You could detect hot spots to find out, okay, is this drawing more current than what I'm supposed to, or is there some kind of an electrical overstress that has happened? So these are semi-destructive mechanisms for failure analysis. You can do hotspot analysis or thermo analysis by with IR pattern and find for or look for any defects in the part. So these are all the physical FA, and we have the capability to do all that. This is Resolve's capability for entire qual, FA, and debug. Along with this, as you saw in the few slides ago, I said we have to build hardware for every aspect of silicon, be it qual, be it failure analysis, be it SLT, be it functional validation. So we have, TESOL has the capability for to build all hardwares, both we can build PCBs, we can build packages, we can do SIPI simulation, we can also build all of the mechanical units needed for all of this hardware. These are some of the tools that we use for our PCB unit. These are some of the high-speed interfaces that we are working with currently. 94% is our net promoter score. So all of this we covered thus far was pre-volume manufacturing activities and flow that we did. We are just trying to showcase here that all of it is available in India, in Bangalore. If we can't do it here in Bangalore, we have capability or partnership with partners outside of India, and we could address any of your requirement. The next is what we have. What Senthil is going to be talking about is high volume manufacturing. Uh, just to let you know, TESOL also has high volume manufacturing capabilities. In fact, these are our test floors. We have a test floor in San Jose. We have a test floor in Bangalore. We have a test floor in Austin. We also have a production floor in Singapore and a small test floor in Malaysia. Our San Jose office has about 893K testers, from the latest exascale to the smart scale. We support about, between our test floors, 20 to 25 different kinds of testers. We always try to see what is the best ROI before any testing is started or before any test is considered. So we do you could consult with us before you start your chip design to see what would be the tester of choice for you. And I think more about testing, Senthil will be talking about what is needed for ATE testing and what the capabilities are. Whatever capabilities Senthil is going to talk about, TESOL supports that. These are all the verticals TESOL has capabilities of. Okay. Sorry, this was a very quick intro. Any questions? Okay, Senthil, you can take over. Hello?
Yes, sir, we
Uh,
can hear you.
Yeah. Thanks, Anand, and thanks for the good show. So hope you can see my screen. Please let me know.
Not yet.
How about now?
No.
Yeah, we can see you.
All right. Okay.
No, sir. I think you may have to reshare it.
Let me share it again.
Because we are able to see your desktop.
Desktop,
Mhm.
maybe it is.
Yeah.
Okay, maybe it is loading little bit in a delayed
Mhm.
way. Means
Can I
Anand,
share it for
you
you?
can stop sharing, Anand. There are two shared screens right now.
yeah, maybe that would be the reason.
Yeah, now it's fine.
Yeah, now we can see Sendil's screen.
All right, thank you. post-silicon validation and manufacturing. So pretty much all the intro, so it's covered by Anand. And first of all, I extend my sincere thanks to the committee, IESA, and also Anand for accepting to share the presentation between us, both Caliber and Tessol together, like presenting this paper. So without further delay, I'm straight away jumping into the flow now. So the very first slide, what you are currently seeing is a test and manufacturing flow. So this is a kind of the full process of post-silicon validation right after the IC design. So here, if you see in this flow, you will see IC design. This is actually followed by the wafer fab. So wafer fab, once the wafer fab is done, we get the wafers, and from the wafers, we do sorting. I will explain what is sorting. From sorting, like we are moving to package, and means we sort the die, and from there, sorted die will go for the package and assembly. Then we will get the final test samples. This final test samples will go to the FT screening. From FT screening, and again, so it is going to the QA, and after QA is done, finally it goes to the customer. So here there are like additionally we have RMAs and failure analysis. So most of the things are actually covered by this RMA and failure analysis covered by Anand. So I will be covering the rest of the stuff here. So I divide this content, this entire flow content into two, software and hardware. So let me straight away go to the initial challenges within this flow, So if you see, most of us are already aware of this. There are like many initiatives the government is taking, and prior to this, all these initiatives, we do have only the manpower and this related skill sets within India. So now, having said that, like we have so many of these initiatives, both front end and back end. So we are now participating or contributing more towards the semiconductor industry. So now, if you take within this industry, what are all the key challenges, right? Like we are going to encounter, or we are currently facing down the line, let us say in next 3 years or 5 years, our main challenges will be identifying the right skill set or skilled workforce, basically test engineers, product engineers, application engineers, maintenance, field service, and technicians. So if you take all these units with huge investments, we will get the material, but how we can address the skill set? So that is going to be quite challenging. And very quickly on these roles and responsibilities of if these engineers, if I give you test engineers, they are the one who develop the test program for screening the devices. Product engineer, they are mainly concentrating on the product yield, care, and all. And application engineers, they are the one who support us for developing libraries, solving any software bugs and other stuff. Maintenance staff, they are the one who maintains the equipments within the test floor. Field service and technician, they are a subset of maintenance engineers. Okay, so there are other scope of engineers within this semiconductor manufacturing projects, but I'm not covering that. But whatever I am covering here is mainly focusing on the post-silicon validation ecosystem. So other challenges within this industry, right? Other challenges, what we see here is the cost and the time. So actually both are interlinked. Cost in the sense is eventually like how much is the cost of the chip and how much the test is contributing. So as Anand already covered, so the majority of the cost is actually covered from the test portion of it. So until this point of time, if you take any product, they are actually getting manufactured and tested outside only because two things, right? One is not having the proper ecosystem, and the other one is not having the required skill set. So now that with all these initiatives, we hope down the line in next 3 to 5 years time, we will have the entire ecosystem within India. And the third challenge, the main challenge, is the supply chain. So this is, I can give you one quick example. Let us say in Singapore, if we are getting some product and it is reaching the airport, the next half an hour to 45 minutes, the product will be on the tester on dock, right? Whereas the same scenario, if you apply here, even though there are some product companies who are having the engineering testers, but then like the way the supply chain works now is not that easy as we see outside. So it will take hardly like 2 to 3 days for us to get the device. And that will be impacting the time to market, because I know design engineers, DFT engineers, DV engineers, they are very much curious about the results. So if any such delay is happening within this ecosystem, it is not acceptable. So that is another main reason until this point of time, like the India is not top preferred for this particular post-silicon validation or this entire semiconductor industry, but the things are changing now. So that is what we can see. There are other such factors to be considered as listed here in terms of test coverage, handler prober models, and compliance with the regular standards. All these are the factors to be considered. So this slide, it will give you a quick gist of the components of any test system. So as Anand covered, he has covered the complete journey of different equipments, and here it is little bit giving you more detail, in-depth detail of what are all the each components we see within the test system. This test system could be anything, ATE or SLT system or a bench system, anything. These components are applicable everywhere. Okay, so let us take hardware. Hardware, you can see probe card, load board, bench board, SLT, burn-ins, eval board, everything, right? So all these comes under hardware category. So I put some examples here. If you see the top right corner is a sample of probe card, and the next one is load board, some burn-in boards, SLT boards, and high-speed RF eval boards, RF boards, everything. So in this hardware development, right, basically there are multiple engineers involved. First thing is a test engineer. He has to confirm based on the requirement of the test plan. He has to confirm and arrive at the test circuitry, which is eventually considering the throughput also, like how many sites he has to take care. And once the design is ready from the schematic is ready from the test engineer, it goes to the design engineer, where the design engineer has to design it based on the schematic, and it will be like a optimized design so that like we can cut down the cost there. And once the design is done, just in case if it is a high speed or high power device, we need to go for simulations to ensure for the quality. Once the simulation is done and all things are verified, then it goes to fab and assembly. And again, it comes back to test engineer for the board bring up. And once the board is bring up, then it is good to go for the production interfacing. Right, let me go back. So software. So software is basically, there are like multiple softwares involved. The main and key software is the actual tester or bench system, the main core programming software. Let us say in 93K means it's a smart test software, and Teradyne means iFlex software. There are like multiple software very specific to ATE, and that is where like we write all the programs based on the test plan and test list. Apart from this main software, like we do have other softwares related to it, like a vector conversion, where we do a EDA type vectors to the tester specific vectors, debug tools like timing diagrams, move tools, pin margin tools, and other softwares like version control, product engineering, automation. All these are quite common with other tester platforms as well. Then apart from software, like we do have instruments. So these instruments are actually, it's not all the instruments should be present for a particular test system. So it is optional, or and we can have n number of devices also based on the number of slots available with each test system. So DC, digital, analog, source and capture, high power, high speed, special instruments like photonics, avalanches. So all these are special instruments, and pattern generator, everything. So the other component is actually the production accessories, where we are talking about the handler, prober, and thermal control unit. So handler is mainly for screening the final test samples, and prober is for screening sorting the die, and thermal control unit is for engineering bring up, where we do all this temperature, controlling the temperature for the device under test. So there is another component, like this is very minor, like manipulator, chiller, compressor. All these are essential for a test system to run actually. Right, let me go to, I'm a little bit running, but considering the time, please stop me whenever you have any questions. So now I'm covering testing based on device volume. So here I break down into 3 different categories. One is prototype testing, low to medium volume testing, and high volume testing. So prototype testing is basically testing alpha samples. In alpha, so this alpha samples I can say is at the early stage of the device, means IP development. Okay, so here we are actually validating the design itself, whether the developed design is working as per the intended functionality. And so this is basically done at some low cost test medium, like benchtop tester or some custom setups, right? And this is mostly manual or semi-automatic, and I can say the numbers of samples are less than 1K units. Okay, whereas in terms of low to medium volume, this is beta samples, and the volume can go as high as 100K. And this is basically, we call this as a pilot runs, where we are kind of checking all the functionality and parametric behavior of the design. So this is just a one step before we actually go for the volume ramp up. And here we can actually cover all the burn-ins, reliability test, and we can cover all the standard test processes the device is intended to compile. And once this volume is decided, once this volume is tested and working properly, then it is actually getting into the volume testing. Volume testing, we always call this as a gamma samples, and it's a full scale production, completely automatic. And here the concentration will be more towards cutting down the cost. How we cut down the cost? By basically optimizing the test time and increasing the throughput, increasing the efficiency. And generally here the volume always goes more than 100K units. But this is just a random numbers, but you can at least categorize this always any volume into within these 3 types actually. Okay, another major role in test engineering, I can say, is a product engineering side, data analytics. So this data analytics is where it is mainly useful. One is on the data collection and the data analysis. So how it is helpful for the volume run. So when you take for the prototype testing or for the low to medium, this data analytics of is helpful, but it's not to that extended level. But whereas when you go for really HVM, high volume screening, This analytics is very, very important, right? So how means with this data collected, we can do the yield improvement. So this yield improvement can be done by three areas. One is by giving the feedback to the test program, doing some modifications or adjustment in order to improve the yield, or the another area is to give the feedback to the final test sorry, wafer set program, where we can do some test program optimization to improve the yield. And the third item is give the feedback to the design fab itself in order to improve the yield. So three stages, there are three stages of control system, closed loop, where we can improve the yield. And operational efficiency and cost reduction, we can also do based on the data, the amount of data collected. How means operational efficiency is sometimes like, say for example, we are designing a CPU with the octa-core, and sometimes we are getting 80% good yield and 20% of devices falling under category only quad core is passing. So there, instead of scrapping the device, we can consider going for down banding. All these kind of cost saving activities, operational efficiency, can be covered using this data analytics. This data analytics is a separate, it's a bigger ocean actually. It's all taken care by the product engineering team, and the front end is all taken care by the test engineering team. So coming to Calibre test capabilities. So in terms of services, I mentioned before also, like Calibre is capable of giving a full turnkey solution. This is a high quality full turnkey solution, when it means like it right from the feasibility all the way up to the production release, reliability and other stuff, everything we are covering. And especially in terms of our business model, like we do all the type of business, like either doing the entire project, bring up and delivering the products, or in terms of providing engineering services, or sometimes modular based support. So all the business model we are supporting. And we have most of our working force sitting in India and in 3 different offices, and we work around the clock. Right. So in terms of domain experience, we are covering the entire ecosystem: digital, analog, mixed signal, memories, PMIC, photonics, RF, and sensor. Then skill set wise, is again, it is going to be, I'm repeating again. So sort, final test, care, qual, vector conversion, platform conversion, throughput improvement, test time auditing, anything you mention, we can cover that within this entire ecosystem. So all under one roof is our concept here. So one key notable point, means with the Calibre, is that like we are actually having a dedicated R&D team focusing on technological improvements, and we are always believing in the deep engineering steps, and there are like many test IPs we are actually working on. One such notable product is that like we are coming up with integrating the ML approach along with the post-silicon validation problem, and we have been doing this for quite some time, and getting recognized by global test forums, and we keep on progressing here in this area, and many customers are welcoming this idea. The thing is that like the main core gist of this particular tool is that we are the ML approach is, the model is capable of generating its own test program based on the trained data when a new data sheet is given. So more detail is shared here, and we are also listing down the list of test forums which is recognizing our efforts, and this is almost like 70% complete, and we are under further development for 30%, and it will be available in the market soon. Allied services, apart from the test services, we are also having allied services, where we cover predominantly on 4 areas. One is the full entire space of hardware design, then package design and assembly, simulation services where we cover signal and power integrity services for high speed and high power devices. Then the embedded system services. In the embedded system, there are like a couple of very notable products that we are actually focusing on. One is reconfigurable test system development and the full turnkey solutions for various small scale chips which is focusing on eval boards, function boards developments and all. So reconfigurable test system is nothing but for a given product, if the volume is huge and the requirement is low to medium complexity, then we are actually developing, we are actually delivering customized architecture so that like we develop our own tester to screen the device, which will be very much cost effective actually. And we have more details. If interested people can approach us directly. Our global footprints, we are headquartered in Singapore and we have offices across the world, and within India we have 3 offices. Majority of our workforces are sitting here in India. Yeah, that's all I have. So with all these presentation, I can say, right, like prior to this initiatives, right, these government initiatives, the awareness of post-silicon validation was very less, but now people started understanding what is the importance of post-silicon validation. But then companies like us, we have started doing these services since the year 2000, and it is like next year, like we are going to celebrate our silver jubilee. So we are already prepared for it, and let us all contribute together for Make in India. Jai Hind. Thank you. So any questions? I'm open, please. Any questions from the audience?
Sir, I would like to ask one question. I am from a university which is offering a BTech program in electronics and communication engineering, and we would like to start a specialization in the field of semiconductor technologies. So I would like to know what kind of labs do we need to set up to meet the requirement of your application designers, product engineers, and the engineers you talked about, the manpower requirement, skilled manpower requirement for your industry, semicon industry. What kind of competencies should be imparted to the students so that they become employable in semiconductor industry? And what kind of lab setup will be required, and what kind of investment will be required to be made by universities?
Okay, that's a good question. I can answer it quickly. So we as a company like Caliber, we are having tie-ups with many institutes within India, including IITs. And we are having that MOU signed up between institute and the company. And we, from our side, corporate is giving trainings to the students there. And the skill set required is mainly, they have to get aware of VLSI testing basics, which can cover both digital and mixed signal stuff. Apart from that, lab wise, having this test setup with from the institute level it's going to be a huge investment. But in terms of when you have a proper MOU signed up with companies like us, means we will cooperate with you, like we will train your students and we can help you hiring the students also. We have to work jointly together to achieve this.
Thank you. Thank you very much, sir.
No problem. Any other questions from the team? Okay, then thanks for all your patience. I'm done from my side.
Hey, 1 minute, Senthil.
Yeah,
There is a
please.
question in the chat window
Yeah.
Okay, sure.
from Chip Edge. We
Yeah.
keep getting inquiries if we can offer training on post silicon validation since testers are costly. We could not think of offering so far. Any possibility of offering this training other than doing in-house training for new hires and similar companies? So let me check if he's still online.
Yeah. So Anand, I'm online.
Yes.
So we keep getting that requirements where some companies are they ask, do you have this training? We need to train some engineers. Since the test equipment is costly, so we have EDA tools which for design we are offering, but we don't have this post silicon related trainings. So since it is a testers are costly, so we didn't think of so far. So what is the feasibility there?
So, Venkat, good question. In fact, we started an paid service last year to do exactly the same thing you're asking. Basically, training people on test engineering, both the test engineering basics and also giving them hands-on fields on the tester. Even though there's a lot of inquiry, people we found very few takers for it. The first session we were expecting about 30 students out of 350 who applied. Only 8 showed up. So we do have a course which we are going to run for a few more batches, but depending on how the market takes it, we may continue or discontinue. Right now there is one course going on with 16 students.
Is that course for public? Anyone can join that course, kind of?
Yes. We had advertised for it in LinkedIn and other places. It
Okay.
is open for public.
And I'm aware TESOL has a college collaborations or university collaborations where you offer certain training to those colleges and our students from those colleges. But so the mentioned program is for open for public. I mean, for anyone to enroll, right?
Yes, you're right. It is open. It's not for anyone to enroll. There are certain minimum criteria that we look for once they register. We do conduct a basic test because we are going to be providing a certificate. So we want to make sure that TESOL name is still held up. So we don't take everybody. It is a selection process, but it is for general public. After they're trained with us, they can go find an employment anywhere they want. It's not bound that they need to work with us.
Okay.
Senthil, this is Poonam.
Yep.
So can we also attend any one of the sessions that you have open for public?
The question is to me.
Yeah, the question is whosoever.
Okay, in fact, like we also have this training programs open to public, and it is all about, like as Anand mentioned, right? Like we need some prerequisite in order to attend the course itself. Once you are eligible, once you can clear that prerequisite screening process, then you can actually pay and apply the training program.
So can you send the invite?
Yeah, sure. Why not? So you can also go through the syllabus, what is covered, what is the time period, and what sort of workshop is we are handling. So everything you can go through there. So I mentioned the email here. Maybe later on, if you wish, you can send me the email. I'll give you the details.
Sure. Thank you.
Thank you.
So thank you so much. I think with the interest of time, we will end here. And we have our president, Mr. Ashok Chandak, sir. So please.
Hi, good evening, everyone. Gautami, can you hear me and everyone?
Yes, Ashok, we can
Please,
hear
sir. Yes, sir.
Great, thank you. So thanks a lot, all the participants and particularly our speakers, Anand and Senthil, for a very informative and detailed discussion. on this topic, which is obviously very relevant in terms of the post-silicon validation as well as the manufacturing India capabilities. As India, has a vision to take further lead in terms of leveraging its design competence towards manufacturing, this topic is obviously very relevant. And there have been several companies, global companies, India design centers, those who have been doing the post-silicon validation in India, and we could call India, particularly Bangalore, has become a hub with many of those companies centered around there, actually, including a lot of testing activities being done by TISOL, particularly, kind of a global leader, I would call. They are the world's largest non-IDM testing facility worldwide, actually. So all those knowledge, experience, whatever has been shared, I'm sure would be very useful for the participants over here in terms of the post-silicon, the testing, debugging skills, the prototyping, the silicon bring up, all very related topics, actually. And as some of you and maybe many of you know, there are a lot of government incentives and policy support that is coming up, both from the manufacturing ecosystem development as well as the design link incentive for the product development and creation. So this kind of technology expertise is going to be surely very important. And for that, Anand and Senthil, thank you very much for putting together great, insightful content, bringing your all knowledge as well as the experience and learnings, sharing with the ISA members as well as non-members if others have joined, particularly in the benefit of industry. And this is how, our industry has grown, actually, where the several colleagues like Senthil and Anand have been instrumental and involved with all of you to share their knowledge and learnings, and we have expanded our industry, and they should continue to grow. So on behalf of ISA management member community, Anand and Senthil, thank you very much for your time, efforts. It's 1 hour program, but I know that putting together 1 hour detailed program takes several weeks and weeks of preparation. So your commitment, your contribution is really very, very valuable. Thanks a lot for that. And also for the audience for joining this particular webinar, getting to know from the experts based on their experience and learning key topics over here. And I'm sure this will be useful for you as you continue to progress into your career in the same field or maybe allied fields. With that, thank you very much. Gautami, over to you.
Thank you so much, sir. Thank you. So once again, thank you, Senthil sir. Thank you, Anand sir. And thank you, each one of you, for joining. Have a great evening.
Can we have contact details, means email ID of Senthil and
Sure. I think we'll put up the recorded link on the YouTube channel.
Sure.
We'll also post this on our LinkedIn handles also. So please follow.
Poonam, the last sheet has both of our email IDs.
Yeah. Sure. Thank you.
Thank you, sir.
Thank you,
so much. Thank you.
Gautami sir. I like your hospitality. Thanks again.
Thank you.
Thanks a lot.
Thank you.